Good morning, everyone, and welcome to the JKMRC Friday Morning Seminar Series. On behalf of the University of Queensland and the Sustainable Minerals Institute, I'd like to acknowledge the traditional owners and custodians of the lands on which we meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to Australian and global society. So for this seminar, it is my pleasure to welcome Oscar Castro. Oscar is a metallurgical engineer from the University of University of Santiago in Chile, and holds a Master's of Engineering Science from the University of Queensland, specializing in hydrocyclone modeling and rheology. With over 38 years of experience in the mining sector, Oscar has held various roles, including academic position at several universities, project manager at CIMM, hydrocyclones manager at Weir Minerals Chile, metallurgical superintendent at Collahuasi, hydrocyclones and valves manager at Weir Minerals South Africa, and tailings planning superintendent at Lumina Copper. He's currently the global product line manager of Performance IQ service as FLSmidth. Oscar also holds multiple invention patents, notably for the new head for the Cavex Hydrocyclone and the Recyclone. Today, Oscar will be presenting a seminar titled Design Process and Hydraulic Limitation of Control Strategies for Flotation Bank Optimization. So please, let's give a warm welcome to Oscar. Thanks, Oscar.
Thank you very much. I'm very honored to be invited to give and share some of my experience in process control and process control applied to flotation. I learned process control, and I got interested in process control since I met Bill Whiten back in the 90s. And then I was trained by Guillermo Gonzalez and applying some of their process control strategies and procedures for nonlinear processes in Mount Isa mines. So one of the basics of process control is to define a strategy, and that strategy should consider the first stage in which you have to stabilize the process. Most of the actual engineers that are involved in process control, they are not a specialist on mineral processing. And on top of that, they are not experts on fluid dynamics and physics and chemistry and so on. And if you do not pay attention to those concepts, you are not going to be able to recognize the limitations of those processes that are associated with the operation and control of a flotation bank. So this presentation is oriented to try to motivate young engineers in order to get involved into the physics behind the process control strategy and the process control process. So this seminar is related to how we are going to be highlighting what are these limitations and how we have to pay attention of that in order to define a proper control strategy for the flotation banks. So despite the fact that there are a lot of advantages in optimizing flotation processes, such as the implementation of new sensors, cameras, new control strategy, and very sophisticated ones, in order to operate individual cells. Nevertheless, when you start paying attention to the complete bank or a complete circuit, things get more complicated. So the performance of the optimization of the complete or the entire bank remains a challenge, and there is no unique strategy that covers all those aspects that I have mentioned. So some of the instruments or new instrument, they do pay attention to some aspect like the color of the froth, the shape of the flow, the froth. They use reagents control, reagents in advance, and most of these strategies, they use pulp label profiles or slurry labels profiles. Nevertheless, if you start asking the operators why they have defined or they have used some specific label profile, most of them, they don't know. They also have in a plant, they defined or the strategies define airflow profiles. And they also don't know why and how and which one of those profiles are the best ones. And some of them, they do not know even if you have to define a specific profile. Most of the common aspects or most of the common beliefs in the operator's side is that you have to try to float the best as you can in the first 3 or 2 first cells. And this is a very common thinking and very common mindsets in metallurgists. And let me tell you something, this is precisely what we have to avoid. And some of them, they have also more recently defined froth superficial velocity profiles. And some of them a combination of what is being defined more recently as the important, like the definition of peak of air recovery per cell. So even though that is very important to define the strategy, whatever is the one that suits you best in the plant, there is no agreement between the metallurgist or between the process controllist in which of those ones are the best for the plant and which one will increase the profit of the project. So some of the aspects that we are going to pay attention here is basically the couple of mechanistic models in which you have a collection zone in the bottom of the cell in which particles get in touch with bubbles, and those bubbles are raised to the surface and get into the froth zone. So on top of that, since you are raising these bubbles with particles in it, you will drag some of the non-valuable material with them. And so the froth will contain the particles which are be purely collected in the collection zone, plus the one that you have dragged through the pulp that are not valuable particles. And then, as soon as you establish the froth, you have to take the froth out of the cell. So the total recovery of the flotation cell will be the multiplication of the recovery at the collection zone multiplied by the recovery on the froth zone. So to put it in white and black and white, if the recovery of froth is zero, the froth recovery, the whole recovery will zero as well. Okay, so if you see in any plant a flotation cell that is not overflowing froth into the launders, you have, at that moment, you have zero recovery. And if that cell doesn't recover at all, the residence time in the bank will be reduced, and the flotation recovery of the whole bank will reduce. So the froth recovery and the residence time of the froth in the cell will affect and will be related to the recovery and the rate of the bank. So if the froth residence time is too short, so all the difficult particles to be floated are not going to be floated. And some of the particles that are coarser are also going to be, will have a very low rate of recovery of that process. So if you go to the other extreme, instead of having very short residence time for the froth, you will increase the viscosity of the froth, you will reduce the mobility of the froth, and you will have a lot of bubble bursting, and then all the particles that are dragged by that bubble will burst, and you will lose the particles that are associated with that bubble. So the residence time of the froth into any cells and into the bank, it is heavily important in terms of what will be the outcome of the whole process. So for this reason, a good control of the overflow rate could guarantee an optimal recovery per cell, and therefore an optimal recovery of the circuit. And this is some of the aspects in which the peak of air recovery, it's is a way to understand, a way to balance how much is the appropriate residence time for that, and how much is the direct flow for that. So typical limitations that you have, or you will have to face within the flotation bank, are physical and chemical limitations. Let me give you an example. Physical limitations are the ones that are related to, let's say, the configuration of the circuit, the size of the flotation cell, the distance between the launders and the position of the froth in the cell, especially on those large, big flotation cells. Chemical limitations are the ones that are associated with pH control, frother dosages, and collector dosages. And also, as you go down into the last, from the first to the last flotation cells in the bank, those chemicals are being reduced because most of the chemical will be associated with the froth that you are going to take away. So if you evaluate the concentration of frother in the first cell and the concentration of frother in the last cell, you will see a large decrease of the concentration of frother. and reagents. So definitely that will impact the bubble size, the bubble stability, and so on. Even the probability of collection. Design and mechanical limitations. Well, the design is, let's give you an example of how many launders do you have in the flotation cell? What is the shape of those launders? How long are they? How difficult are, or how, if they are good, properly associated, or if they, do you have enough number of launders, and if those launders are properly sized by the amount of concentrate that you will need to extract from those cells. Mechanical limitations are associated to some of the aspect of maintenance. So the lip of the launders sometimes get, when the slurry gets dry, you are going to build up, a bunch of dry slurry into the lips, and then it will be an obstacle for the froth to get into the launder. So then you will have mechanical limitations. So mechanical limitations are also the ones associated with the, let's say, the mechanical issues of the dart valves, or if the dart valves are, get trapped because they have, they do not have an appropriate maintenance. Kinetic limitations. Well, kinetic is very associated with the bubble size and with the bubble, with the reagents concentration, and also pH, froth concentration, and collector concentration. So obviously the kinetic of the first cells are quite different from the kinetic of the last cells, because as I mentioned, the reagents the concentration of reagent is reduced from the cells, the first cell into the last ones. So hydraulic limitations, these hydraulic limitations is the one that I'm going to give examples, but the profile of the bank, and how much is the hydraulic jump, or the jump between the first one to the second one, and so on. So if the cells, first cell, are in the same level, on the same floor level, horizontally speaking, then you will not have enough potential energy to move by gravity the slurry from one cell to the other one. So this is a very important aspect, and if you don't pay attention of this one, you will not be able to control the level, especially the difference of level, of froth level and slurry level between the cells that are in the same floor. So then you have how the surface tension or the froth concentration will affect the bubble lifetime. So if you have low concentration of frother, the stability of the froth will reduce, the size of the froth will reduce, and the residence time, or the bubble lifetime before the bubble burst, it will be reduced. And these are the graph. It tends to show you how this is important in terms of surface tension, in terms of lifetime of the froth of the bubble into the cell. So I will show you a video in which you will have to pay attention on the shape and the bubble bursting from the first cells to the last cells.
The froth in the first few cells of a bank is often heavily loaded with hydrophobic particles. The froth appears dense and heavy. The bubble size is small due to the stability imparted by the particles. As you move down the bank, the appearance of the froth will change. There are not as many hydrophobic particles available to float, and thus the froth loading is lower. Windows appear and froth stability decreases, resulting in larger bubbles, many of which will burst.
So this is one of the key aspects of what we are talking about. So you can see in the last cells here, those black zones are what the professor there calls windows. So that area is not covered by concentrate. And the slurry, it's also an agent in which it is a stabilizing agent. So if the particle, if the bubble is covered by concentrate, the bubble and the froth will be more stable. So you can see in those last part of the video that those froth, those bubbles which have windows are the ones that are going to burst first. Okay, so and this is because the concentrate is also have been evacuated from, most of the concentrate have been recovered in the first cells. So if I do have a strategy which pay attention to recover all the concentrate in the first 3 cells, the last cells are going to be, the froth in the last cells are going to be very unstable. And regardless of the set point of froth level that you establish, you are not going to be able, physically, you are not going to be able to reach it. So the full strategy will fail because you will have a very unstable froth, because as soon as you start not achieving enough froth height, the dart valves will start trying to close too much. And then the dart valves are going to be beyond the limit in which you may have a cavitation of the valves.
The froth in the first.
So one of the aspects that I want to emphasize here is the one that that the froth, the froth layer or the froth height is a consequence of how much bubbles are you generating and how much bubble are bursting in the first place.
The bubbles at the base of the froth are similar in size to those rising in the pulp. As the bubbles move up through the froth, some coalescence occurs and the bubbles become larger. As bubbles arrive, each layer is progressively pushed upwards, the froth builds, and the height increases. Eventually, the rate of new bubbles arriving at the base of the froth will equal the rate of bursting, and the froth height will stabilize. In practice, the froth height, also known as level, is controlled by removal of froth into launders and by moving the position of the froth-pulp interface.
So you saw here
hydrophobic particles which.
So you saw here that in this photo, you will see that if the froth is not overflowing into the launder here or into the tray, so, and there is a maximum, physical maximum of froth height that you can achieve into any flotation process. That means that there is a physical limitation. So if you put here a limitation or a level of froth that goes beyond these physical limits, you're not going to be able to achieve it. So if your strategy does not consider this aspect, you will fail in terms of a system that will start trying to achieve something that is physically impossible. So the limitations that are associated with the mechanical limitations are basically how much is the distance between in any position in the froth towards the peripheral launders. The particles of the froth that are close to the peripheral launder, they have to travel just 20 or 30 centimeters. But in a large cell, like the ones that we are designing in these days, which are in the range of 650 cubic meters, sometimes they have to travel more than 2 or 3 meters in order to reach the outer launder. So that froth is going to be more unstable because it's going to be bursting, or the residence time of that froth, that part of the froth that is far away from the launder, the peripheral launder, will have a residence time quite different from the one that is closer to the peripheral launder. So that's the reason why we have invented those launders, or the physical launders. Yeah. The other important issues is the type of flow into the which is associated to the type of mechanisms that you're considering. So here you see two types of cells. That a typical cell that is a Wemco cell in the right, which is does not have forced air injected and is induced by the vortex in the rotor. They do have different flow patterns that the ones which is the left and the one that you have forced air. So the froth patterns in the left one is opposite to the is counterclock. In the one in the right is the opposite. So where do you put the peripheral launders is very important as well. And that's the reason why a cell that is auto-aspirated, it does need different type of launders than the ones that uses forced air, because they have flow patterns that are reversed. So design limitations are associated to, well, the need that you have radial launders, and how do you calculate them? Okay, some of the methods that we use are very empirical, and there are a couple of them which are the froth carrying capacity and the lip load. So you normally calculate how much concentrated are going to recover, or how much is the mass recovery of concentrate in your flotation application. And then you will see that there is some patterns, so there is some good practices in which you are using those two parameters, and if those fall into the benchmark, then you will see, and they will tell you how many launders do you need for that application. But it's not a physical chemical calculation from basics. So those are the typical values that we use in order to consider for the froth carrying capacity, which is for rougher is 0.8 to 1.5. For a scavenger is 0.3 to 0.8, and for cleaner is 0.10 to 2. And for the lip loading, it's less than 1.5 tons per hour per meter. So these are the ones, the typical values that no one have established. What is the physical meaning of those numbers? Those numbers, they happen to be the ones that most of the companies or the designers use because it's a good practices, but there is no physical calculation in terms of why those numbers are meaningful or what they mean. So launder capacity, it is an important aspect because that will tell you, it will impact the residence time of the froth in the cell. So kinetic limitations, if we decide to have, a strategy that is orientated to recover copper, probably copper, because it have a kinetic, it have a faster kinetic than molybdenum. So you will, obviously you will have, you will lose a lot of molybdenum in this flotation cell. So you have to have an appropriate strategy for all the valuable components of your flotation process. So on top of that, the number of cells and the residence time that you are allowing by defining different froth labels, the volume, the actual volume in the cells will change. So let's put it in an example. If you have a very large, froth label, so you will reduce the total volume of the bank. So, and in the opposite side, if you have very narrow froth layers, you will increase the froth or the residence time for flotation, and some of the last cells will recover a lot, but the grade will be suffering because grade and recovery in a flotation bank are linked. So if you increase the recovery, you will decrease the grade and vice versa. So the layout of the cells are very important, and how much is the distance between the first cells one and what we call it the hydraulic jump. So from the first cells here coming into the second one, you do have an hydraulic jump. So you have this label, and then the second one is beneath that one. But the second and the third are in the same level. So are you going to be able to have exactly the same froth label in this one and this one? How you are going to control that? So most of those ones, if you don't pay attention, some of these ones are not going to overcome. The froth is not going to overflow into launders in the same way. Sometimes this one is not going to float at all. So paying attention of the profile and the inclination and how your circuit is established by the engineering company, it will restrict the way that you have to operate the flotation bank. These are typical limitations or typical profiles of configuration of profiles in different companies around South America. You see that, well, some of them, like Pelambres, the big cells, 250 cubic meters, they have a configuration, what we call it 1, 1, 1, 1, 1. So you will have an hydraulic jump from the first to the second one, and so on. Every single cell we have will have an hydraulic jump. So, but establishing hydraulic jump between cells for large banks is more costly because you have to have a kind of more costly installations. But considering that any plant, or most of the plant, they do have different profiles, then, and you apply the same, can you apply the same strategy for all of them? So that's a question, okay? And this is why, you know, so if you have, so you cannot have the same height in those cells that are in the same floor. The distance between this and that, or establish the potential energy from the fluid that will be the driving force to go according to this theoretical balance equation, energy balance equation, in order to overcome the resistance and the friction losses and the losses of quite restrictions that you will have to face between one cell to the other one. So if this difference in height is not enough to consider the friction losses that you are going to, will not have movement from this point to this one. So there will not be enough pressure drop here or pressure difference in order to overcome the friction losses. So another aspect that you have to consider is the friction losses at the dart valve, and how do you operate the dart valves. So the flow coefficient that tell you how much is the friction losses that you will have and how much is the flow that you're going to have as you close the valve. It's also have to be considered in order to be in the region in which this is feasible in order to overcome the friction losses that you are going to have here. And also, you cannot froth or you cannot close the valve to a point in which you will reduce the velocity between cells 1 to cells 2, and to a point in which you are below the critical settling velocity in in the connection boxes. So, or on top of that, this area in which this is not completely not linear. So you have to operate this dart valves between a window, which is a physical window. Typically, if you read the manuals, they will tell you that you have to operate between 20 to 80% of the stroke. But sometimes you will have to define particle settling limitations, or what will be the velocity or the speed of the slurry between the two cells, and in which you will have such a velocity that will be below the settling velocity, and then you will have sanding problems. Or even worse, in which if you close too much, especially the last dart valves, in order to achieve the physical froth level that you wanted to achieve, and you can have cavitation limits. And most of the engineers do not have, they don't know, they don't be aware that you can have cavitation in a valve. So the potential energy between two cells, the continuous cells, is quite important. So the definition of potential energy is also affected by the air holdup. So even though that you may have difference in froth levels from one cell to the other one, you will be able to, if you put too much air in the first cell, then you will not have enough energy to overcome the frictional losses. So you will see a lot of strategies and papers around the world in which they tell you what is the importance of this establishing froth levels, and they propose different methods of optimization of the process control. Some of them are the airflow profile, some of them are the pub profiles, but some of the ones that I like more is the froth stability issue, okay? So froth stability, it tells you that you have to somehow take your concentrate out of the cells, out of the bags, in a very sort of proportional way. Do not take all the concentrate in the first two cells, because you are not going to have enough concentrate in order to cover the froth in the last cells, and you're not going to achieve, and then you will have too much bubble bursting, and then you will not be able to reach the froth level that you are going to have. And some of the strategies that are most likely in that path are the ones that are calling the profile of maximum air recovery. So the maximum recovery per flow of air in the cell. So this is it tells you if you inject, X amount of volume of air into the cell, how much air is it will be ending in the concentrate. So if you calculate the concentrate that goes into the launder out of the cell, though you will have, in other words, you will be able to measure somehow how much bubbles are bursting, and that is going to be a measurement of froth stability. So this is a method that tells you how it's an indirect measurement of measuring froth stability. So there are multiple control strategies for flotation cells back. Many of them are, generating significant improvements in both recoveries and grade. But if you do not pay attention on those limitations that I have mentioned during this presentation, you are not going to be able to reach or to achieve what you have theoretically defined as the best strategy. So this is an invitation to the physicists and metallurgists and mineral processing guys in order to get involved in those mechanisms that define those limitations, in order to cooperate with the process control guys and process control metallurgists in order to both together define the best process control strategy. Okay, that's about it. I do not have too much time, so it's 45 minutes. I try to put all this concept in just 45 minutes. Thank you.
Right.
If there is any questions.
Thank you very much, Oscar. It's a very nice presentation. Even for me, I'm a geologist, to know a little bit more about flotation, its limitations, and how to mitigate some strategies. So I'm gonna open for some questions on the audience. All right. Well, first.
Thanks for your presentation, Oscar. It was a really good one. I really like the fact that you mentioned that nowadays when you go to operations, you notice that the engineers that are on site, might not have the proper know-how on how to get the cell up to a standard. What strategies do you have in place as an original equipment manufacturer to address those lack of knowledge when you sell an equipment and commission the equipment on site?
Be very honest that this is a quite new approach, and normally the strategy is not part of what a cell provider gets involved with. Okay, so normally the strategy is set by the engineering houses on engineering local process control engineers. And unfortunately, there is a gap here in which some of the engineering houses, they don't allow you, a metallurgist, to tell them how to define process control strategies. And this is something that is very challenging, and because they tend to think that you don't have anything to contribute in order to tell them how to define a good strategy. And this is why I'm trying to, motivate the cooperation of these different specialties, because a long time ago, when I was in I don't know how it is now, when I was at the JK, we used to have, and cooperate between different specialties to define these kind of things. But in these days, what I have seen and what is my experience, I don't know what about in Australia, but most of the time, the strategies are associated with, or that defined by the so-called experts that normally are electronic engineers, that they do not have too much knowledge into these physical, chemical, hydraulic, and fluid dynamic aspects. So basically, this is something that we do afterwards. It's an after sales kind of application. And this is the reason we have formed this group of process control experts in order to support the implementation of new technology and new ways of helping customers to optimize their processes. But this is definitely something that we have to work with to improve it.
Hi, Oscar. Thanks for a very good presentation. Just interested in your views on, I think there's been quite a few advances in computational fluid dynamics over the last 5 to 15 years. Do you think there's a role here for trying to understand the physical limitations of the system by using CFD techniques?
Definitely. So if you see what I have mentioned there, it's the limitations of the flow patterns. Those flow patterns that you have seen in those videos are precisely defined by CFD. So why some of the launders that we establish in, let's say, WEMCO cells are completely different from the ones that are the ones for forced air flotation, because precisely we have calculated using CFD models in order to see how the flow streams are moving the froth into different areas. And that's the reason why we have, those cylindrical launders or in one case, and we have radial launders in the other case. And we have, by practical meaning, we have defined different kind of launders for different applications. And then we have started to understand a lot better by using those techniques. So CFD is quite definitely a good example of that. And it's quite complicated because you have, you don't have water there. You don't have slurry, you have air, you have particles, and you have water, and you have, chemical reagents there. So, but right now, the power of the computers and the techniques that you use for, let's say, those models that you use for solving Navier-Stokes equation with CFD are especially in for those models that establish different kind of turbulence models implemented already into more of the most common CFD packages. Just to give you an example, to solve the fluid of using CFD to solve Navier-Stokes equations for a cyclone, a very small cyclone in the 90s, just to run one go, it took us like 2 months. You can do exactly the same right now in a few hours, or a few minutes.
All right, thank you. Any other questions on the audience? I'll just ask a question, Oscar, on the side of geology. How can us geologists that have some knowledge of mineralogy, geochemistry, how can we help the metallurgists and mineral processing people on flotation strategies, or how can we bridge the gap? Any advice?
Well, it's the mineral is the most important part, So flotation processes are not, an exception of that. And today, geologists are very important to define and to help us to define a good geometallurgical model. Because if you're floating different minerals, we do have to have different control strategies. And we use just one type of control strategy. But just give you an example. Imagine that you are running a plant or a new ore body that is quite new, geologically speaking. And you will have a lot of clay. And if you have kaolinite in the circuit, the whole thing will change because the viscosity will change and the kinetic, the flotation kinetic will change, the froth stability will change, the mass recovery of mineral will change, the grade will change, everything will change. The consumption of reagent will change. So definitely you are going to be critical as a geologist in order to determine, your model or a way of mitigating some of the minerals that are going to complicate flotation process, like blending or whatever, You guys in the geology side will play an important role in order to define good strategies for the mineral that we are going to face in the flotation process.
All right, feel important right now. Thanks very much, Oscar. Fahana has a question online. So could you please explain what kind of changes occurs in water when you add frother in it?
Well, as soon as you start adding frother, the surface tension of will change, okay? And if the surface tension changes, the amount of bubbles and the size of the bubble will change. On top of that, the frother will give you more stable froth, and the bubble bursting will change. So from the water point of view, the most common issue will be the important role of reducing the surface tension. And surface tension, for the same amount of air, you will reduce the size of the bubbles, and the size of the bubbles are going to, as you have more air into the cell, because you will increase the probability of impact bubbles with particles. You will reduce the racing time of the bubbles into the froth, and you will capture more air. The air holdup will increase, and air holdup change the kinetic constant of flotation. So frother will place most important roles in the mechanistic or in the fluid dynamics of the froth and the bubbles in the flotation cell.
All right, so I think that's it. I'd like everyone, thank you very much, to thank Oscar for his nice presentation today. So thank you, Oscar. And next week, we'll have Lisette Vester with the seminar Size Matters, Development of a Laboratory Fluidized Bed Flotation Device, the JKHF Mini. So hope to see you all there, and thank you.